Okay, now I'm going to discuss the feedback loops, which I just introduced in the last few minutes as being a matter of great concern and something that is really critical for you to understand why we are so concerned about anthropogenic climate change. Now, I ended with a different version of this one. This is actually the Vostok ice core only goes back about 350,000 years. And we can see these ice ages. The peaks are the interglacials, the valleys are the ice ages, and we're up here at another peak today, you can see. And of course, one thing that is notable here is our our level of CO2. This is 300. We're about here. Okay, and that kind of tells you that in the last 350,000 years, we've never had this much CO2 in the air. Okay, now why did such tracking occur in the past? Is it possible today? The reason that the tracking occurred was because of feedback loops. When the temperature went up because of solar radiation, because of the Milankovitch cycles, it caused a release of CO2. When the temperature started falling because of, again, solar cycles, the CO2 was taken out of the atmosphere. They're linked, okay? And what that means is if we put the CO2 way up, and if it causes warming, which we undoubtedly know it will, then we'll get into these positive feedback loops. So let's take a look at what's going on. What causes the CO2 to go up as the temperature goes up? Now, some feedback loops are tied to directly to heating, and some are tied directly to the release of more CO2. One that's tied directly to the release of heating is water vapor. So as the climate warms slightly with the CO2 release, we already said 1.2 degrees Celsius doubling of CO2, and that occurs if no feedbacks occur. So when we eventually hit equilibrium, if there were no feedbacks, that's all the warming we would get. And we would just have the radiative forcing of additional CO2. However, we know already that we've had feedbacks from water vapor. In fact, the warming that we've experienced is faster than what we would sort of expect to have experienced, and it's because of water vapor. Now, this is how it works. Higher temperature of the atmosphere leads to more evaporation from oceans and wetland surfaces. Probably more importantly, and please write this down, it is also tied to the effect that warmer air can hold more water. The hotter the air is, the more water it can hold. And so if this happens, the air warms a little bit, more water vapor is held, and that causes warming. Okay? Now this water vapor will double the temperature increase estimate. So the estimate of 3 degrees Celsius for a doubling of CO2 is from radiative forcing of the CO2 itself and the radiative forcing of the extra water vapor that we're going to get with that warming only. So this feedback loop alone, if it is operational, will lead to an increase of 3 degrees Celsius on average if we double our CO2 levels. And that would mean 560 parts per million. Now, water vapor gets into the atmosphere, and this also affects clouds. Okay, clouds interfere with transfer radiation in the atmosphere in two ways. First off, they reflect a certain proportion of solar radiation back to space. They have a very high albedo. I mean, they're very bright, and they reflect, and this reduces the energy available to the system. So clouds cause cooling. And if you've flown over clouds in an airplane and looked down, it's extremely bright if you're above the clouds. And so you can well imagine that's a lot of reflection going on, a lot of cooling that takes place. But if you get these really high clouds, or clouds that can actually be up in the stratosphere, these act as a blanket to thermal radiation from the Earth's surface. So they absorb thermal radiation that comes up from the planet and then emit that radiation back, causing warming. What we tend to see with this water vapor is daytime cooling, because the sun doesn't get through, but we always get nighttime warming. So complex way that the water vapor works in the clouds. Now, what effect will dominate? So water vapor alone will cause heating. If the water vapor doesn't get changed into a cloud, it causes heating. And so that will happen, okay? But if we look at the cloud effect, it turns out that cloud height is what's most critical in whether a cloud warms or cools, because the cloud height affects its optical properties. If it's really high, all the particles are ice. If it's really low, the particles could be water. How thick is the cloud? What is the size of the cloud particles? All of these things influence how light passes through it or is trapped by it. Low clouds tend to cool, and high clouds tend to blanket. And you should remember this, okay? Low clouds cool, high clouds blanket and warm. And jet contrails cool. That's the little moisture that comes out the back of a jet plane. Now, this is a simple diagram I pulled off the internet. It just shows high clouds trap more heat because they let a lot of that radiation passes through them. They're thin. Their properties are they allow the light to pass through, but then they trap the heat that's coming back up from the surface. Low clouds reflect a lot more sunlight, and so they tend to cool. Now, most clouds cool. From this diagram, we can see this is the sort of, I don't know if it's an average or when it was taken, but it shows that if you look at this, most of the areas are somewhere between green and magenta, okay? And so if we look up here, we can see that, Ohio, we actually have some nice cooling clouds up here. They cool us off. In parts of the ocean, it's cool. But then if we look at Africa, we're getting warming there. We're getting warming in China and the Himalayas. Certainly getting warming in the Arctic and the Antarctic. And so, this is where we have our high clouds. And so that's where the warming is. But most of the clouds are cooling. So that's actually kind of a good thing for us. Now, the oceans play a major role in existing climate. Their thermohaline circulation is very critical and causes the ocean and atmosphere to be strongly coupled. Meaning, the oceans really determine our climate. Okay, evaporation from the oceans is the main source of atmospheric water vapor, which is the largest heat source for the atmosphere. So it releases this water. It releases heat, and it is actually this vapor is going to cause the air to warm. So we really have a large heat source in the atmosphere, and it comes from the ocean. In a warmer climate, there will be more water vapor. But the question comes, what's going to happen to the clouds? Will there be more low clouds? Or will they be about the same? Or less low clouds? And this has been the source of the scientific controversy as to how much warming can be expected. If you have more low clouds, the warming won't be as intense. If you have more high clouds, the warming will be much more intense. And recently, people have been modeling this and also getting empirical data from what's happening in cloud formation. And the disturbing news is there will be less low clouds. Okay, and it's in effect. I understood the paper when I read it, but essentially, all of this extra water vapor is going up into the upper atmosphere and forming clouds there. Now, this means that the estimates for the amount of warming we can expect with a doubling of CO2 have gone up. It used to be the estimate was about 3 to 5 degrees is what we would expect with a doubling of CO2. Now it's 4 to 5. Yeah, it was 3 to 4. Now it's 4 to 5, and This is not so good. We're getting closer to the estimates that Svante Arrhenius had, and it's just not good. 4 degrees of warming is devastating. It's catastrophic. 3 degrees of warming, I would say, is catastrophic. 2 degrees is what the nations of the world have agreed we need to stick to. You know, it's like saying, no. It's not realistic. So warming ocean feedbacks. You will actually, as the ocean warms and the surface waters of the ocean have been warming, we've documented this, there'll be a decreased absorption of CO2 by the oceans. So warmer water holds less CO2, and if the water warms, it won't pull CO2 out of the water as much, out of the air as much. That's a concern, because that means we're going to have less CO2 being sequestered, more of it in the atmosphere, more of it warming. So the water vapor one was a direct heat. It heats it up, and then that heats it up, and then that heats it up. This is, you heat up the ocean, it doesn't take out the CO2, which gives more heating, you get less CO2 taken out. It's that kind of cycle. This is a CO2 temperature cycle. Acidified ocean. So some areas of the ocean are becoming acidified due to excess CO2 in the atmosphere. And this could lead to a decrease in calcified organisms that can no longer precipitate calcium carbonate. I've already discussed coccolithophorids, and if we pull less CO2 out of the oceans, this is the same effect. Okay, we had ocean acidification, and we have this effect of warmer oceans. We're just not going to be able to pull the CO2 out of the air, and so we will get more warming, and then we'll pull less CO2 out of the air. Okay, so this is a CO2 cycle. Warming and methane clathrates. Okay, so methane can become complexed in water ice, and these sometimes are called methane hydrates. That's an incorrect term. Please use methane clathrate. Okay, they're kept in the sediment by high pressure and cold temperatures. This is essentially we're taking natural gas and freezing it in a complex with water, and then under the high pressures and cold temperatures of the ocean floor, it's stable. However, if it gets less pressure or if it gets less cold, they could be released. Now, the Arctic methane clathrates are considered the biggest risk right now. These clathrates are in many areas of the oceans, but the Arctic is a concern because the Arctic has very shallow seas, and these are under less pressure, and therefore we could get, a lot of release. Now, methane in Siberia has been increasing, and this is possibly tied to methane clathrates. So there's 100 times normal levels that have been detected. We don't know if, what part of it is methane clathrates and what part of it is decomposing permafrost. Both of these release methane. Siberia has a lot of permafrost and has a lot of shallow seas. So hard to know exactly where it's coming, but the levels are going up. And the methane clathrate release, sudden methane clathrate release, is thought to be responsible for the global warming that caused the end Permian mass extinction, where 95% of the species went extinct. Now, this happened 55.8 million years ago. It was the biggest of all extinctions, and there were probably lots of things that happened. So not only was there a methane clathrate release, there probably was a hydrogen sulfide release, which is a toxic gas as the oceans warmed. And there were a lot of things that went on in the end Permian, but methane clathrates were probably part of it. Now, one that was mostly methane clathrates was the Paleocene-Eocene thermal maximum. This was caused by, they think, an earthquake that destabilized a huge shelf of marine sediments, which slid down, released their clathrates, and you had this gigantic release of methane clathrates. And then these warmed the climate, and then more methane was released, and this warmed the climate, more methane was released. And so over a period of 20,000 years, the temperature actually rose by 6 degrees Celsius. Now, what's interesting is the pessimistic estimate of what we could achieve in the next 100 years is a 6 degrees Celsius increase. So we could do in 100 years what it took over 20,000 years to do at the end of the Paleocene. That rise led to the extinction of the benthic foraminifera and led to an irradiation of many mammal species. So we had a big extinction event with 6 degrees over 20,000 years. Over 100 years, plants and animals can't adapt. That time frame is so fast that there will be much higher extinction than we had at this extinction event. The rate of carbon increase in the atmosphere was almost equal to the rate of anthropogenic release today. So, but we had warming for a long period of time. This is the Paleocene-Eocene thermal maximum. And what's kind of interesting is we can see, here it is right here. So right between the Eocene and Paleocene. And extinction events often define the ages. So essentially the difference in the Paleocene and Eocene is this big extinction event that occurred due to this warming. And they found the geological evidence of where these methane clathrates were released, where this earthquake moved the sediments. Went way up over a period of 20,000 years, then it came down, and then it continued to warm, and then we came down here. This is kind of interesting because we see an Antarctic glaciation, Antarctic thawing, Antarctic glaciation, and then now we're in our current Ice Age Earth cycle. Now, this is 65 million years of climate change, so, we're looking at, after the dinosaurs died out, what was happening, okay? It's a long time frame, and, so there has been warmer climates, but if we were in this climate, we probably wouldn't be surviving because it's so much warmer than what we have right now. Now, ice albedo feedback. Ice has a very high albedo, meaning it reflects light back into space. And as it melts, it exposes land and water, both of which absorb more light and heat, reducing reflectivity when, and then it then warms. And so this is one that this doesn't affect the CO2, this affects the temperature directly. Light comes in, more of it is absorbed by the oceans and the land. You have more radiation back into space. It's trapped, and you have more and more warming. And so this is one that concerns a lot of people. This is probably already occurring. Permafrost melts and lakes disappear. So this has been happening. Organic matter in the soil breaks down, and then the methane and the carbon dioxide are released. And we expect that up to 70,000 million tons of methane could be released in the next few decades from permafrost and soil. And these greenhouse gases lead to more warming. Organic soils of boreal forests will also likely decompose faster. Soils in England are losing carbon at a rate of 13 million tons per year, which is equivalent to the Kyoto Protocol reduction of 12.7 million tons per year. So this is a paper published in Nature and caused a lot of concern, at least to me, when it came out, because what it says is England, which has been a very good player in terms of climate change, they have, they signed on the Kyoto Protocol, they built their windmills, they increased the fuel efficiency of cars, they increased the, the insulation on their buildings. They saved 12.7 million tons per year. They actually achieved their Kyoto goals. It was completely undone by their soils decomposing and releasing CO2 and methane. This is something that we're going to see and talk about later, but there is a point where we might reach where these feedbacks kick in, and it won't matter what we do. We won't be able to stop the train. Forest loss causes problems. I mean, we have forest loss when we cut down tropical rainforests or other forests. That is a source of CO2 to the atmosphere. But the biggest concern we have right now with this is forest fires. So the rates of forest fires have greatly increased in the western United States. We'll certainly look at this when we get to the west. And with a forest fire, you have a sudden carbon input. I mean, all this carbon goes in the atmosphere. You don't hold it in the wood anymore. And the primary fear is that drought in the tropics could lead to fires that cause conversion of the Amazon tropical rainforest to Caatinga, which is this scrubby forest that doesn't support very many animals and plants and is not a very nice kind of environment, would not be good for us as well. And so we could lose our Amazon rainforest because of forest fires. Now, all of those, I think there were 7, were positive feedbacks. There are some negative feedbacks, so I need to go through these. Soot and particulates from burning coal shade the earth and cause cooling. It's sulfates that are released from burning coal, and they also seed cloud formation. So when we burn coal, we produce a lot of these aerosols that shade the earth, and so some of the warming from the CO2 from coal is offset by the cooling from the aerosols, essentially the air pollution from the coal. Okay, these aerosols are what are thought to have cooled the climate from 1950 to 1970. So they are a significant effect. Now, evaporation is less with aerosol shading, and we actually have a term, aerosol cooling. And that has to be incorporated into climate models, and it has been. So now our current climate models use aerosol cooling as part of their calculation. Now, this is what I would like you to do with the end of what we have today. I'd like you to turn to your neighbor, to a classmate. If you're sitting all by yourself, go find a group and sit with them. And what I want you to do is figure out, in your opinion, what is the most convincing skeptic argument you've heard against climate change. Now, if you don't find any of their arguments convincing, then give me which one do you find the hardest to counter. So I'm sure you have friends, peers, associates, family members that say, climate change, So which one of these skeptic arguments that they use do you find hardest to refute, to counter? And after you talk in your little groups, write down the best ones. Give me the ones that you think are the best arguments, and then give those to Dr. Rosenthal. And sometime in the next couple of weeks, I will try to address these and make sure you understand how to counter these arguments. So don't sign your name to these. Just give me the arguments, and that's what we will do